We're going to be looking at chemical equilibria. Okay, now this is a topic that the vast majority of you did at GCSE, but not all of you. It's also the top end of the understanding at GCSE, and so what I'm going to do is I'm going to take it from the beginning and ensure that you understand everything you need to understand about equilibria. You will have come across this at GCSE with either the Haber process, okay, for the majority of you, or the contact process for those of you that did GCSE chemistry rather than double science. Okay, but I will go through it from scratch. We're going to be looking at dynamic equilibrium. We're not going to be covering equilibrium constants in any detail, and we're going to cover something called Le Chatelier's principle. We will talk about the Haber process in some detail. So, to begin with, if you were to plot a graph of the concentration of reactants and products over time, you might end up with something like this. And what this shows is the concentration of the reactants decreases, and that's not really surprising. It means they get used up. Yeah? As the reaction is progressing, the amount of reactant is decreasing because it's getting used up. That's pretty straightforward. At the same time, the amount of the product increases. And what you see here is that initially the rate of reaction is quite fast, and over time the rate of reaction decreases. And that's what you'd expect, because as the reactants get used up, the concentration gets lower, and the lower the concentration, the slower the rate of reaction. And you know that from GCSE. Okay? But you've probably not seen a graph like this where it shows both of them. And what this shows is the reactants all get used up, and you form a certain amount of product. And the amount you form is dependent on the amount of reactant you had to begin with. Okay? It doesn't just carry on going. You don't carry on making product out of nothing. It's going to level off when all the reactants have been used up. Happy with that? And if you double the amount of reactant, you'll double the total, or if you double the concentration of reactant, in this case because it's concentration, you will double the total product. Okay? If you were to halve the concentration of reactant, you would halve the concentration of product, and so on. Yeah? Assuming it's a one-to-one reaction. So, this reaction here is assuming 100% conversion. And there's some slides to help you. And this is what I was meaning. Well, this is where it's a bit different. Okay? The amount of reactants, well, the concentration is still decreasing. The concentration of the products is still increasing. But crucially, the concentration of the reactants doesn't go to zero. Okay? And the concentration of the product doesn't go to the theoretical maximum. And what this means is that the reaction has progressed, but it's only gone so far. It's reached a point and then it's stopped. Okay? You happy with that? And this is because the backward reaction starts to occur. As the reactants get used up and products formed, so the backward reaction, i.e. the products turning back into reactants, starts to happen as well. Okay? And you end up with a balance between the two reactions, where the reactants are turning into products and products are turning into reactants, and the total amount of both of them stays the same. Does that make sense? Yeah? To begin with, the forward reaction is happening faster than the backward reaction, but eventually they level out. And the two reactions occur at the same speed. And this is called a dynamic equilibrium. And it's important to note that the total number of moles of product and reactant stays the same, but also the reactions are still occurring. The products are turning into reactants, the reactants are turning into products. If those reactions are both occurring and the total number of moles stays the same, what must be true of the rate of the forward reaction and the rate of the backward reaction? It's equal. And what we've got here is a dynamic equilibrium, where the forward reaction is occurring and the backward reaction is occurring, but they are occurring at the same rate. Okay? So, at equilibrium, the backward and forward reactions are equal and opposite. So, This is called a dynamic process. A reversible chemical reaction is a dynamic process. Everything may appear stationary. The masses may, or the moles, sorry, may appear to remain the same, but actually you've got a dynamic situation where you've got forwards and backwards occurring, but at the same rate. Importantly, the position of the equilibrium can be varied by changing certain concentrations. Thank you. Okay? And this is where the rubber hits the road at AS. Okay? How do we change the position of the equilibrium to maximise our yield? Okay? And at A2, you look at how we do that mathematically. So summary of so far. When a chemical equilibrium is established, we've got reactants and products present. The equilibrium can be approached from either side. What that means is we can start with the reactants and end up with an equilibrium that's got some products in it. Reaction is dynamic, so it's going forwards and backwards, and the concentrations remain the same. So the number of moles remains the same, but both reactions are happening and at the same rate. Okay. We're not going to do this bit, this is A2. Instead, we're going to skip forward to Le Chatelier's principle. Le Chatelier basically said, when a change is applied to a system in dynamic equilibrium, the system reacts in such a way as to oppose the effect of the change. Basically, whatever you do to an equilibrium, it does the opposite. It doesn't explain why, but it does explain what happens. In other words, if you heat up an equilibrium, it will move in the endothermic direction to try and cool down. If you cool down an equilibrium, it will move in the exothermic direction to heat up. If you pressurize it, it will depressurize it. If you depressurize it, it will repressurize. And so on. Okay? Basically, whatever you do to an equilibrium, it moves in such a way as to counter the change that you make. Okay? So, we're not, as I said, we're not going to be doing the equilibrium constant. That's A2, so we'll skip through that. Okay. Let's look at factors affecting the position of the equilibrium. If we've got this scenario where reactants move to products and so on, if you increase the concentration of reactant, okay, so if you add more of that, okay, then it will try to decrease the amount that it's got. Does that make sense? Yeah? If you add to it, it will try to decrease. It will do the opposite. Therefore, how can this reaction decrease the amount of reactant? Well, it can use some of it to make the product. So if you add more reactant, it tries to decrease the amount of reactant by moving the equilibrium to get more product. Make sense? Yeah? And thus re-establish the equilibrium. If you decrease the concentration of reactants, which way is the equilibrium going to go? Left or right? Left. Do we understand that? Did I just lose anyone? If you decrease the concentration of the reactant, the equilibrium will move left. I.e., some of the product will turn into reactant. Are we happy with this idea of move left, move right? Yeah? If I increase the concentration of a product, it will move left, as it says so there, and decrease concentration of a product, it will move right. Okay? Happy with that? All this move left and move right means is that if we say it moves right, we're saying some of the reactants turn into products. Overall, there is a decrease in reactants and an increase in products. So, if we increase the concentration of O2 on the equilibrium position, as I predict the effect of increasing the concentration, if we increase the concentration of O2, equilibrium is going to move left or right? Right. Okay? If we decrease the concentration of SO3, the equilibrium will move right. So if we want to make SO3, we add lots of that, and we remove that as it's formed, which is exactly what's done industrially. Happy with that? Okay. In both cases, it moves to the right. Now, pressure. very simply, if you increase the pressure, it tries to decrease the pressure. Okay? And for reasons that I'm not going into but pop up in A-level physics, it is not about the size of the molecules, it's about the number of molecules. So if an equation has got 3 molecules on one side and 2 molecules on the other, and you add pressure, okay? If you add pressure, it will try to decrease the pressure, and it will move to the side with the fewer molecules on. Okay? If you want a very quick A-level physics explanation, okay, every molecule, you can assume it's an ideal gas, and every molecule occupies the same volume. Okay? Because it's all about the volume the molecule occupies in terms of it moving around in space. And it doesn't matter how big the actual particle is, because the amount of space that it has to itself, on average, remains the same. Okay? So, increased pressure moves to the side with fewer molecules. Decreased pressure moves to the side with more molecules. Got that? Okay? So, if we increase the pressure on this equilibrium. Now, for some reason, I've never quite worked it out, pupils really struggle with this question. On the left-hand side here, how many molecules have I got? I heard a 2 there before I heard a 3. The answer is 3. Okay, I've got 2 of that one and 1 of that one. And on the right-hand side, I've got 2. Okay, so if you increase the pressure, it's going to try to decrease the pressure by moving to the side with the fewer molecules, so it will go right. You all happy with that? Okay? And if you increase the pressure on this one, how many molecules on the left-hand side? 2. How many on the right-hand side?
2.
If you increase the pressure, no effect on the equilibrium position, because you've got the same number of moles on both sides. You happy with that? Okay. And we're all good there. Right. Temperature. To work out the effect of temperature on an equilibrium, you have to know which way is exothermic and which way is endothermic. So, if the reaction is exothermic, okay? If it's exothermic, you heat it up, it's going to want to cool down. If you heat it up, it's going to try to cool down. It can cool down by going in the endothermic direction. Basically, you have to imagine that you've got a sealed vessel, okay? You've heated it up, and it's now going to try to cool down. And it will cool down by reacting endothermically and taking some of the heat that's causing the particles to move around really fast and form chemical bonds that absorb some of that energy. Okay? Did I say make chemical bonds? Yeah, break chemical bonds. Okay, got that the wrong way around, sorry. It will move in the endothermic direction and thus absorb heat. Okay? Happy with that? You sure? So, if you heat it up, it will move endothermically. So if the forward reaction is exothermic and you increase temperature, it'll go left. Yeah? You heat it up, it goes in the endothermic direction. If the forward reaction is exothermic, then the backward reaction is endothermic. So if the forward reaction is endothermic and you heat it up, it will move to the right. Got it? Yeah? I'm seeing quite a few nods. I'm seeing a few people sort of snoozing now. Okay? This is not particularly hard, but it's very fiddly. It's very easy to get it wrong. Okay? So, the reaction is exothermic. And you heat it up, it will move in the endothermic direction, which is the backwards reaction, and therefore it will go left. So, here, delta H is positive. Exo or endothermic? Endothermic, okay? Because the products have got more energy than the reactants. If you increase the temperature, is the equilibrium for this one going to go left or right? Hands up for left. I want everybody voting on this one. Hands up for right. Okay, pause please. This bottom one, if delta H is negative, exo or endothermic? Exothermic. Therefore, if I increase temperature, which way is it going to go? Hands up for left. Hands up for right. Pause tape. So with this one, it's exothermic, so it's going to move in the endothermic direction, which in this case means it's going to go left. You heat this one up, you get less sulfur trioxide. Catalysts. Importantly, catalysts don't affect the position of the equilibrium. Okay? What they do is they speed up rate of attainment of equilibrium. Okay? By providing an alternate pathway with a lower activation energy. And what you've got here is your Maxwell-Boltzmann distributions. Okay? This is basically saying you have a lower activation energy. Critically, a catalyst does not lower the activation energy. It provides an alternate pathway with a lower activation energy. And you can see that here in terms of your enthalpy change. Rather than having a big old activation energy there, you've got a smaller one with an intermediate and then another one. Okay. So, does not affect the position of the equilibrium, that's what I said a minute ago, but it does increase the rate of attainment of equilibrium. The Haber process is covered in the majority of GCSE. So, it's about forming ammonia from nitrogen and hydrogen. How many molecules on the left-hand side?
4.
4. How many on the right?
2.
Therefore, do we want to use a high or low pressure if we want to make ammonia? If we want to make ammonia, do we use a high or low pressure? High. We've got 4 on the left, 2 on the right, so if we add pressure, it will try to depressurize by moving to the side with fewer molecules. So high pressure. That's all good. Exo or endothermic? It's exothermic. So should we use a high or low temperature?
You want compromise.
No, I'm not getting there yet.
Low in theory.
Low in theory, because it's exothermic, and if you heat it up, it's going to go left. Yes? So you cool it down, and it goes right. We happy with that? Yeah, use a nice low temperature, and you get lots and lots of ammonia. There is a problem with that. What's the problem with using a low temperature? Sorry? It takes longer. Absolutely right. Okay, so, key word that you used at the back was compromise. There is a compromise between rate and yield. I.e., you want a temperature that makes it quickly, but gives you enough. Okay, now, the way I try to explain this is in terms of rugby. It is better as a team to score 3 drop goals a game than 1 try and a conversion. Yes? In some scenarios, it's better to do a little and often than it is to do a great amount very slowly. Yes? And with the Haber process, a compromised temperature is found, okay, that allows a little bit to be made, but it's made quickly. Okay? And that's the compromise between rate, how fast, and yield, how much. Catalyst, okay, iron. And we've gone through all of those, and we've talked about that, and there's your compromise. Why is the Haber process so important? Well, you can make nitric acid from ammonia, and you can then combine ammonia with nitric acid to make ammonium nitrate, or ammonia with sulfuric acid to make ammonium sulfate, and these are both really good fertilizers. This one has the advantage that it's not explosive. Okay? This one can be quite dangerous. And that is equilibria. Are there any questions about it? No? Okay, if we can stop the tape, please.